Hello and welcome back. In this lesson, we're going to take a look at simple harmonic motion oscillators in terms of extracting information from a position versus time function. Let's begin. First thing we ought to know is the generic equation for a simple harmonic motion oscillator. Well, if it's a cosine graph, then the general equation would be x is equal to a times the cosine of omega t, where omega can be expressed as a couple of things. One, it is the 2 times the pi over the period, and it can be represented as the square root of k over m if we're talking about a simple harmonic motion oscillator mass attached to a spring, or it could be g over the length of the pendulum if we're talking about our simple harmonic motion oscillator being a pendulum. Well, we don't know what type of oscillator we're dealing with yet, so let's just keep them all in mind, okay? Now, another thing we talked about in our last video was how to come up with the other functions, other meaning velocity and acceleration versus time, from your position time function. There were 3 patterns. First pattern, we alternate between sine and cosine. So if our position graph is cosine, our velocity graph is going to be sine. Now, since all 3 graphs have the same period, all 3 functions and graphs have the same omega. The second part of the pattern is if we transition from sine to cosine, the sign of the function remains the same. If we transition from cosine to sine, however, like we are in this example, you switch the signs. Since this is positive, this becomes negative. The last, of course, is we multiply by 1 factor of omega each time. So technically, there's omega to the 0 power right now. So we're going to begin this one by multiplying by 1 factor of omega, or omega to the first power. And this is our velocity as a function of time for a simple harmonic motion oscillator. Acceleration, we follow the same rules. We're going to alternate between sine and cosine. So we're at sine, we're going to alternate back to cosine. Same period, so same omega t. Since you're going from sine to cosine, the sign of the function remains the same. Since it's negative, it stays negative. And we multiply by 1 additional factor of omega. So this becomes a omega squared. So those are the 3 functions that we need. Now, one thing to note, if we are trying to calculate the position at any time, or the velocity at any time, or the acceleration at any time, it's very important to remember to have your calculator set to radians mode, okay? It has to be in radians mode. Okay, here's an easy test to see if you're in radian mode. All calculators have a pi button. So if you take the cosine of pi, your calculator should spit out a -1 if you are in radian mode. If it does not, then switch your calculator to radian mode. Consult your owner's manual if you do not know how. Well, there's really 2 things we want to be able to extract from any function, and that is your amplitude and your omega, which is, of course, your angular frequency. But from your angular frequency, you can see we can also extract the period. We can extract and calculate for the spring constant, the length of the pendulum possibly, even the mass. There's a lot of things we can get from the angular frequency. So, the first step is identifying what's given in this problem. The number in front of cosine is your A. So what is the amplitude of the oscillator? A in this example is 0.20 meters. The cosine, the value in front of t is your omega. So we know that omega in this example is pi over 2 radians per second. And we're going to need that. The period of the oscillator, since we know that omega is pi over 2 radians per second, and since we know omega is equal to 2 pi over the period, we can switch these out and we can solve for the period. 2 pi over omega. 2 pi over 2. Well, that's the same thing as 2 pi over 1 over pi over 2, which is the same thing as 2 pi over 1 times 2 over pi, right? We multiply by the reciprocal of the bottom. Cancels, cancels, and we can see we end up with a period of 4 seconds. So what that means is all three of our functions and waves that result from these functions, position, velocity, and acceleration, must repeat every 4 seconds. What's the frequency of the oscillator? Well, frequency is just the inverse of the period, so 1 over 4 or 0.25 hertz. Okay, what is the maximum velocity of the oscillator? Well, we can get max velocity by going A times omega. It's the amplitude of a velocity function. Well, A was 0.20. Omega was pi over 2. And so if we go pi divided by 2 times 0.20, we get roughly about 0.31 meters per second. What's the velocity at time equals 2.5 seconds? Well, that's when you have to take your velocity as a function of time, which in this case, it's going to be negative a omega sine omega t. And you need to plug in. Remember, a omega, you just found it. It's the maximum velocity. So negative 0.31 sine of omega. So omega is pi over 2 times the 2.5 seconds. Remember to be in radians mode. So multiply pi over 2 times 2.5, take the sine of it, then multiply times 0.31. So we're going to go pi divided by 2 times 2.5. We're going to take the sine of that function, and we're going to multiply by negative 0.31. And we get roughly about 0.22 meters per second at that instant. The maximum acceleration can be found by going a times omega squared. Remember, maximum acceleration would be the amplitude of the acceleration function. So 0.02 meters times pi over 2, but don't forget to square it. So we're going to go pi divided by 2, which is about 1.57, square that value, and multiply that times 0.2, and we get a maximum acceleration of about 0.49 meters per second squared. Now we're told what type of oscillator it is. We're told it's a mass oscillating on a spring. So therefore, find the force constant, which is K. Well, we know that omega is equal to the square root of K over M, which is the same way of saying omega squared equals K over M. Multiply both sides by M, and K would be M times omega squared, which is our 10 kilogram mass times pi over 2 and square it. So we're going to take pi divided by 2, which is 1.57. We're going to square that number. Then we're going to go ahead and multiply that by 10, and we get about 24.7 newtons per meter. And you can round it up to 25. That'd be fine too. The displacement as a function of time can be found by using the original equation. So A cosine omega t would be 0.2 cosine of pi over 2 times 2.5. So we're going to take pi divided by 2 times 2.5. We're going to take the cosine of that value, in which case we get negative 0.707, times 0.2 is roughly about negative 0.14 meters. The maximum kinetic energy can be found by going 1/2 times the mass times the maximum velocity squared, which would be 1/2 times 10 kilograms times, well, we can use the max velocity we found right here, 0.31. 0.31 meters per second. Again, don't forget to square it. 0.31 squared times 10, take half. And we're looking at roughly about 0.48 joules of maximum kinetic energy at the equilibrium position. So what's maximum potential energy? Well, guess what, ladies and gentlemen? It's the same, just at a different location. Maximum potential energy at the amplitude equals maximum kinetic energy at equilibrium, which is 0.48 joules. And since these are the only two energies, since these are the energies that are only found at, let's say, the equilibrium or the amplitude position, that means the total energy, which is the sum of the two, must also be 0.48 joules. Okay, and so let's go take a look at what this might resemble if we were to plot kinetic potential and total energy as a function of time. Okay, so I'm not going to worry about this half of the graph because time can't be 0. So what we're going to do is we're going to start off at 0 right here, and remember, ladies and gentlemen, the graph repeats every 4 seconds. So I'm going to go, let's see, 1, 2, 3, 4, 5, 6, 7, 8. I'm going to call that 4. 1, 2, 3, 4, 5, 6, 7, 8. I'm going to call that 8. 1, 2, 3, 4, 5, 6, 7, 8. That'd be 12. So I can repeat the graphs a total of 3 times. Okay. I'm going to go, let's see, 0.1, 0.2, 0.3, 0.4. That would be 0.5 joules. Okay, so over in the side here, I'm going to make E be represented with black. I'm going to represent kinetic energy with blue, and I'm going to represent potential energy with gray. So my total energy would be the same, 0.48 joules all the way across. My kinetic energy, however, is going to be, since we are at time equals 0, at time equals 0, we are at a, let's see, we are at the amplitude position. That means at time equals 0, we have a maximum potential energy. So I'm going to make a dot here. I'm going to go to 4 seconds. I'm going to make a dot here. I'm going to go to 8 seconds. I'm going to make another dot. I'm going to make another dot. And all I have to do is just create the wave that goes up and down and repeats every time it gets to one of those dots. So I've done 3 consecutive cycles. The kinetic energy is exactly the opposite of that. I'd have a dot here, I'd have a dot here, a dot here, and a dot here, because I have, at the time when I have maximum potential energy is the time when I have 0 kinetic energy. So So my graph will look exactly the opposite. It'll repeat every time you get down to the blue. And there's our graph of kinetic energy, potential energy, and total energy as a function of time. And finally, let's take a look at position, velocity, and acceleration as a function of time graph. Remember our basic functions. Position is A cosine omega t. V was equal to negative A omega sine omega t. And A, the acceleration, was negative A omega squared cosine of omega t. Let's see what we have to work with here. The amplitude, okay, what was the actual graph? So the amplitude and the omega was pi over 2. The amplitude was 0.2. So x was 0.2 cosine of pi over 2t. V. Now, A omega was V max. So negative, where was V max? 0.31. So negative 0.31 sine pi over 2t. And lastly, max acceleration was 0.49. So A was equal to negative 0.49 cosine of pi over 2t. All three of these have a repeating period of 4 seconds. So what I'm going to do in this picture is I'm going to go a certain distance. I'm going to call that 4 seconds. So actually what I'm going to do is I'm just going to complete 2 cycles of this, okay? So I'm going to go halfway on the picture, make that 4 seconds. I'm going to go the rest of the way and make that 8 seconds. So I'm going to complete 2 complete cycles. I'm going to do that for each picture, for each graph. 4 and 8. 4 and 8. Okay. And of course, that being 0. Okay, this one would be position in meters as a function of time in seconds. Now, this one is position is proportional to cosine of t. Okay, position is proportional to cosine of t. So therefore, we're drawing a cosine function. Remember, cosine functions start at the amplitude. Right here, at time equals 0, they start at the amplitude. So there's your basic cosine wave. Now, you just have to make sure it repeats every 4 seconds. So in other words, the graph ought to look like this. There's 1 repeat. There's 2 repeats. Okay, now, if I'm being a little bit more careful, then I do this. I make a dot everywhere it's supposed to repeat, and then I can make another dot at the halfway point to show where it's supposed to be on the other side. So this is a little bit more accurate look at what the 2 cycles of the position as a function of time graph should look like. Now, the velocity graph. The velocity graph was supposed to be, okay, so I'll do this one in blue. The velocity graph was in meters per second. Time still in seconds, same period, same repetition. We're going to repeat 2 cycles, and it has to repeat every 4 seconds. So Now recall, guys, for the velocity function, velocity varies with the negative of sine of t. Okay, so velocity is proportional to negative sine of t. So what does a negative sine graph look like? Well, if a sine graph starts at 0 and goes up, a negative sine graph starts at 0 and goes down. And it needs to go down in such a way that it's going to repeat. So what I'm going to do is I'm going to put an x at the halfway point. So this is showing where it needs to cross the axis again, which means I should get down to this point. I should get up to about this point. I should get down to about this point, and I should get up to approximately this point. So your wave ought to look like this. There's one repetition. There's two repetitions, 2 cycles of your velocity as a function of time. Okay, and lastly, we're going to work on acceleration. So now acceleration was measured in meters per second squared. Time measured in seconds. And if we look back at the acceleration function, acceleration varies with the negative of the cosine of the graph. So acceleration is proportional to negative cosine of t. Okay, so what does that mean? We have positive cosine that starts here, negative cosine starts at the negative amplitude and goes up. Okay, it needs to repeat every 4 seconds. So starts there, repeats 4 seconds, repeats again at 8 seconds. Here it's at the halfway point. Here it's at the halfway point, something like that. Right? And there's our negative cosine function, acceleration as a function of time. Now, one thing to make these sketches, because these are really just sketches, they're not really graphs. Graphs are made a little bit more accurately to plot actual points. We're sketching the general trend of the graph. Now, to make it a little more accurate, however, we should include the amplitudes for each graph. What do I mean by that? Well, I'm going to go back. I should put a 0.2 here and a negative 0.2 here to represent the amplitude of the position time graph. Similarly, my amplitude for velocity, my maximum velocity, was 0.31. So I should be putting about 0.31 here and negative 0.31 here. And I could even put 0.30, right? And just, I may have stretched the graph a little above and below that. That's fine. But again, this is a sketch. It's not a complete graph. A complete graph would have very scaled axes, okay, that are scaled to very specific intervals, not actually specific numbers. A sketch, on the other hand, I can put pretty much whatever I want as far as the amplitudes are concerned. I can, as long as they're labeled, that's the important part. And then lastly, if you recall, 0.49 was the maximum acceleration. So I go down to the A graph and about 0.49 and negative 0.49 accordingly. All right, and this is showing how to make position, velocity, and acceleration time graphs from simple harmonic motion oscillators.